All right, good morning. So today is the final topic of chapter 5, which is thermochemistry. So today we're going to talk about what are called standard enthalpies of formation. Okay. The symbol for standard enthalpies of formation is a delta H, which is a change in enthalpy. And then we put a little F for formation, and then a degree sign to refer to the term standard. Okay, so the degree sign in this context means that this is being done under standard conditions, or it's being measured in terms of standard conditions. F can have different meanings. So F sometimes means fusion, which is what happens when something freezes. But in this context, it means formation. So you're forming something. And then delta H is the standard enthalpy, or delta H is the enthalpy change. So sometimes they're called standard heats of formation too. We'll use that term. And remember, the reason you can do that is because under constant pressure, if the pressure is constant, the enthalpy change is equal to the heat exchange, right? So Q sub P, it's got to be at constant pressure, right? For a constant volume, then what we do is we say this, we say delta E is equal to QV. So at constant volume, we calculate the internal energy change, and then at constant pressure, we calculate the enthalpy change. Okay, so let's talk a little bit about what this means, the standard formation. So the idea is that we do know that certain processes are associated with energy changes and with enthalpy changes, right? So for example, if you freeze ice, there's an energy change, a heat change that occurs, an exchange of heat. If you melt ice, there's an energy exchange with that as well. Same with boiling or vaporizing, we call that, or condensing water, condensing liquid water. So here's an example of what I mean by that. So it turns out, like if you take water in the solid state, right? So it's ice, right? And we're going to assume it's at one pressure, constant pressure. It takes energy to melt ice, right? I mean, we all kind of have that idea, right? Like it takes energy to melt ice. Ice doesn't just melt on its own. You have to put in energy, right? And so what happens is you get liquid water, right? Ice turns into liquid water. And there is an energy change associated with it, a heat exchange. And we're going to say that it's actually around positive 6. I think I have this 6.02 kilojoules per mole. Meaning that if you have a mole of ice, it takes 6.02 kilojoules of heat to melt it into liquid water. Now that's assuming the atmospheric pressure is 1 atm, okay, 1 atmosphere. And I believe that's also at 0 degrees C. So the temperature is at 0 degrees C, okay? Likewise, you know, if you take liquid water and you freeze it into ice, here's what happens. We just change the direction. Remember what we do when we change the direction? You change the sign. So it becomes exothermic. So actually, freezing water, if you take a mole of water and freeze it, you get energy out. It's exothermic. It releases heat to the environment, to the surroundings. In fact, farmers sometimes use that because what happens is if it gets too cold at night, the leaves on a tree could be damaged, right? Or fruits could be damaged. So in places where it doesn't really get that cold, like you might have one frost during the season or 2 frosts during the season. So overnight it gets cold enough that it freezes. What you can do is you can spray water on the plant. And then if that water freezes on the surface of the plant, it releases a little bit of heat. And some of that heat goes into the plant, which protects the epidermis or the dermis of the plant, right? So you can't do that if it gets real cold, because if it gets real cold, like really cold, then what happens is it freezes, it only releases enough heat to help a little bit, and then the plant gets too cold and it dies. But there's not much you can do in that case anyways. So endothermic, exothermic, right? Same thing for water, for boiling. So it turns out if you take liquid water and you raise the temperature to 100 degrees C and the atmospheric pressure is 1 atm, you can vaporize it, you can boil it, right? Boiling water. And so delta H for this is, I want to say it's 44 kilojoules per mole. Okay. Endothermic, right? It takes energy to boil water. Water doesn't just boil on its own, right? Well, if we lower the pressure of the atmosphere to a low enough value, it actually will boil on its own. But at atmospheric pressure, you got to put in 44 kilojoules of energy, of heat, in order to boil that water. Likewise, when water condenses, so when it goes from a gas to a liquid, now you got an exothermic process, right? So now it's minus 44 kilojoules per mole. Right? So condensing water releases energy, which is interesting, in the form of heat. Okay. Now, what I want to talk about is that degree sign. We're going to look at chemical reactions in a moment, but I want to talk about the degree sign, which I'm calling it the degree sign, but what it means in this context is standard conditions. Okay. The issue here is that I noticed when I was describing these processes with water that I kept referring to the atmospheric pressure, right? I kept saying that it's 1 atmospheric pressure, right? 1 atmospheric pressure. And the reason for that is because that actually has an effect on the value. If you change the pressure of the atmosphere, these values are no longer valid. Likewise, if you change the temperature, they are no longer valid. But they're less dependent on temperature than they are on pressure, but there sometimes is a dependence on temperature that could be significant. So temperature is also an important context. Furthermore, look at it this way. Like this is solid going to liquid, right? And it's 6 kilojoules per mole. This is liquid going to gas and it's 44 kilojoules per mole. So the state of matter has an effect on this, right? So for example, if I said, you know, this is a solid and I'm going to a gas, this value wouldn't be 44 kilojoules anymore, right? It would be some other value. Actually, it turns out it'd be 50 kilojoules because it turns out it's additive. Going from a solid to a liquid is 6 kilojoules per mole. Going from a liquid to a gas is 44 kilojoules per mole. So that means that going from a solid to a gas is 6 plus 44, which is 50 kilojoules per mole. It's additive, right? But the point is that it wouldn't be 44 anymore, right? Going from a solid to a gas. So that tells us that the state of matter is important, right? But the state of matter depends on your conditions, right? Liquid water, you're not going to see liquid water pooling around if the temperature is negative 100 degrees C. It's going to be solid ice, right? Furthermore, you're not going to see solid water. You're not going to see ice if you're on Venus where the temperature is 800 degrees Fahrenheit, right? There is no, you know, there's no ice on Venus. It's too hot for that. So the temperature can vary. So what happens is the state of the matter changes based on the temperature and the pressure. So how do you deal with this? What you have to do is you have to define the conditions. You have to say that this value that I'm quoting you here is only valid under specific conditions. It's valid at this temperature, it's valid at this pressure, and it's valid if the material is in this particular state. That state could be a solid, it could be a liquid, it could be a gas, but we're going to define it for a particular state. And that's where the degree sign, the standard conditions, comes into play. What we're saying is the value that we're quoting here, the value that I'm listing and referring to, is only valid under standard conditions, under standard states, okay? So what does that mean to say they're under standard states? Well, in general, most of the time, when we're talking about standard conditions, typically, we're going to quote it at 298 Kelvin, so that's the temperature. And 1 atmosphere is the pressure. Okay, that's what you're most often going to see. But more to the point, what we would do is we would use our understanding of our everyday experiences of materials. So for example, if I said, I have oxygen gas. You all know what oxygen gas is. It's that stuff we breathe in. So at 298 Kelvin and 1 atmosphere, what is the state of oxygen? Is it a solid? Is it a liquid? Is it a gas? Is it a plasma? Is it a superconducting material? Well, oxygen gas is what we have in the air. Now, usually the pressure around us is about 1 atmosphere, right? Might be a little bit more, might be a little bit less, but it's around 1 atmosphere. Furthermore, the temperature outside is often not that far off from 298 Kelvin, because remember, 298 Kelvin in Celsius would be 298 minus 273, which is 25 degrees Celsius, right? That temperature is actually 25 degrees C. That's pretty close to room temperature, 20 degrees C. So really what this is saying is, what is the state of oxygen gas under the conditions that we normally exist in on the surface of the Earth? And the answer is it's a gas, right? It's a gas. It's not, we don't breathe in oxygen liquid oxygen. It'd be kind of cool if we could. We don't breathe in solidified oxygen. We breathe in oxygen gas. But oxygen is not a gas at negative 100 degrees Celsius and 10 atmospheres of pressure. It's actually a liquid, right? So the conditions are important. So what we would say is that at this pressure and temperature, it's a gas, okay? So if I have some kind of reaction, H2 gas plus O2 gas going to H2O liquid, I'm gonna balance it, okay? The delta H that you're gonna get here is gonna be different from the delta H that you would get here. This is a G, by the way. Make that a liquid. Okay. This will be a different delta H. It will have a different value because this is in liquid form. Okay. The state of matter is important. So when we say standard conditions, what we mean is the state of each reactant or product is going to be the one that we would expect at this temperature and this pressure. So let me show you a few. What about hydrogen? Would you expect hydrogen to be a solid, liquid, or gas at room temperature and atmospheric pressure? And the answer is, well, think of the Hindenburg, right? The Hindenburg was a big balloon back in the 1930s that blew up in New Jersey after coming over from Germany. And that big Zeppelin, it was hydrogen gas, right? It was essentially under normal conditions, 1 atmosphere of pressure and room temperature, it was a gas. So under standard conditions, hydrogen is gas. But think about another material. So for example, let's take carbon, right? Carbon. Now, what's an example of carbon? Well, there's actually 2 common examples of carbon. One is diamond, right? Diamond is pure carbon, right? Or pretty pure. So what is diamond at room temperature and 1 atmosphere pressure? It's a solid, right? So it's a solid. So I'll put a comma S here to say that it's a solid. But there's another form of carbon that you're definitely familiar with. You just may not recognize it as carbon, and that is graphite, right? Graphite is the stuff that your pencil lead is made out of, right? Pencil lead is not made out of lead. Lead is a soft metal, but it would rip the paper. But it looks like lead, so we call it pencil lead, right? So graphite is actually a form of carbon. So graphite, what is that at room temperature and atmospheric pressure? Well, it's also a solid, right? Graphite is a solid. Now, graphite is not a solid. Again, if you go up to, 2000 degrees Celsius and, 150 atmospheres, it probably liquefies at some point. You'd have to look it up and see, but it's a solid at room temperature and atmospheric pressure. So the key here is that what we're doing is we're trying to say what these states of matter are. Is it a solid, liquid, or gas? Because if it's a solid, instead of a liquid, that will change your delta H value. Okay, so standard conditions is the state of matter. Now, it turns out that we can think of what's called the standard enthalpy of formation in the following way. Okay, delta HF degree sign, standard enthalpy of formation. We're going to kind of look at it from this perspective. You take an element, so I'm going to call it E1 for your element, react it with another element, E2, to give you your compound, C for compound. Okay? If we have a 1 in front of this, and the state of matter is what you would expect at 1 ATM and 298 Kelvin, right? Then you balance the equation. So you're going to put coefficients in here to balance the equation, but we want to ensure that this is a 1 here. Then the delta H associated with that is the standard enthalpy of formation. If this is a 2 or a half, then this is no longer the standard enthalpy of formation, it's some other enthalpy. If it's not balanced, it's not the standard enthalpy of formation. And if the state of matter, actually of all of these, are anything other than what you would expect at 1 atmosphere and 298 Kelvin, then it's no longer the standard enthalpy of formation. So here's an example. Water at room temperature, the standard condition is it's a liquid, right? The standard state of water is a liquid at room temperature. So if I take hydrogen gas and oxygen gas and convert that to liquid water, and then you balance it with this being a 1. This has to be a 1, okay? The way to do that would just be to say, let's put a half here, right? So 2 hydrogens, 2 hydrogens. A half of 2 is 1, so you've got 1 oxygen. So it's balanced, and this is a 1, right? Now, and the states of matter, right? This is a gas at room temperature. This is a liquid at room temperature. So now we would say delta H of formation. And whatever value we put, which is negative 285.8 kilojoules per mole, okay, that would be the standard enthalpy of formation, okay? Now, suppose I changed it. Suppose I said, I'm going to balance it in a different way. Okay, that's a perfectly fine equation. It's balanced, the states of matter look okay, but this is not a 1, it's a 2. So that's fine. You can have an enthalpy change for that. In fact, in the previous section, we learned how to calculate what the enthalpy change would be. However, we would not call this delta HF degree sign. You wouldn't use that symbol. You could call it delta H, you know. You could even call it delta H degree sign. But to be the heat of formation under standard conditions, this has to be a 1, okay? And the states of matter have to be what you would expect at 298 Kelvin and 1 atmosphere pressure. So let me take a look at the Alex problem for this. So it says really what they ask you to do is you're writing a standard formation reaction. It's really you're writing an equation. They call it a reaction. I disagree with calling it a reaction, but people use those words interchangeably. Okay, let me show you. Let me show you what it looks like. There you go. Okay. Write a balanced chemical equation for the standard formation of gaseous hydrogen cyanide. Okay, so you're going to write an equation, a chemical equation. You're going to want to put the states of matter in there, and it's got to be balanced, and the product has to be 1 mole. The coefficient has to be a 1. So you have to balance it in such a way that it balances, but you've got a 1 as the coefficient for the product. Now, remember, way back in chapter 3, when we were talking about balancing equations, you know, like Alex was insisting that you have, you know, whole numbers for everything, for all the coefficients. Well, this shows that's nonsense right now. We can see that that's not how we're doing it. We're not going to be able to balance this chemical equation and have everything be whole numbers and still be the standard formation of reaction, right? Standard reaction of formation. We're going to have some fractions in there to make this work. So that's perfectly fine. But I just wanted to point out that often in general chemistry, we give misleading information at the beginning, in chapter 3 in this case. Okay, so yeah. Okay, so the product that we want is HCN. And they tell us it's gaseous, so we know it's that. So here's how you do it. You write that as the product, and you don't have to worry about there being more than one product. This formation equation is just one product, and they're going to tell you what the state of matter is most likely. So what's the next thing you do? The next thing you do is you identify the elements that are in that compound. So it looks like it's hydrogen, it's carbon, and it's nitrogen. But remember, some of the elements are diatomic, 7 diatomics, H2, N2, F2, O2, Cl2, Br2, and I2, right? So these are both diatomic, okay? What about carbon? Is that diatomic? It's not, right? There's only 7 diatomics. Carbon's not one of them. Now the next trick, so let me put them down. So you put H2 plus C plus N2, right? So those are your reactants. We're gonna have to balance it, but we also have to get the states of matter. So, you know, you can look these up, but we all recognize that at room temperature, hydrogen is a gas. So is helium, right? But helium is not gonna be part of the compound. Nitrogen, that's what's in the air. That's a gas also. But what about carbon? Well, we just went over carbon, right? Carbon is essentially graphite. So that would be a solid. So we've got the states of matter in there. Now we just balance it. So the way to balance it is to say, look, we need 1 hydrogen. So I'm going to put a half here. A half times 2 is 1, right? We need 1 carbon. Well, we already have 1 carbon, so that's good. We need 1 nitrogen, so put a half in front of it. A half times 2 is 1. And there you go. There's your standard enthalpy, your standard formation equation, right? You're just writing the equation. We're not doing any calculations with enthalpy yet. We'll do that in the next problem, right? But what this says is that if we look up a value of delta H of formation for HCN, the value that we find is going to be based on this equation. You take a half a mole of hydrogen, 1 mole of carbon, half a mole of nitrogen, you combine them, have them react, and that will give you 1 mole of HCN, and the delta H of that reaction would be right there. Okay, it's kind of interesting. Let me show you another example. Okay, same thing, balanced equation, standard formation of reaction. This is going to be solid calcium oxide. So in this particular example, there's only 2 elements we have to worry about. We have to worry about calcium, and we have to worry about oxygen. Now, what's the state of matter of calcium? Calcium is a metal, right? So you pull out your periodic table, you look up calcium, it's element 20, it's in the 2nd column, it's an alkaline earth metal. Those are all solids, right? So, you know, metals are solid. There's 1 metal that is not a solid under standard conditions, and that's liquid mercury, right? Mercury is a liquid, right? So mercury would be a liquid, but all the other metals are solids, okay? So that's easy enough. Oxygen, that's easy, right? We already did oxygen, that's O2, right? So let's take a look. So calcium oxide. So we're gonna form calcium oxide. It tells us it's a solid, which it should be, right? That's an ionic compound. Ionic compounds are salts, right? They're gonna be solids. So we have 2 elements. We have calcium and we have oxygen, but oxygen is a diatomic. We know that oxygen at room temperature is a gas, and that calcium is a metal and it's not mercury, so it's a solid. So how do we balance the calcium? It's done. Calcium's already done. It's the oxygen that is an issue. We only have 1 over here. So just put a half here, right? A half times 2 is 1, right? If this were O3, that's called ozone, then you just put a third in front of it, right? A third times 3 is 1, because you're just trying to get 1 over here. So you're just multiplying it by a fraction such that when you multiply it by the subscript, that gives you the number that you have on the right side. Okay, let's see if we can do one more. These are pretty easy. I'll show you one more though. So this one, they want titanium 4 chloride. So TiCl4, right? So they also give you the name. Okay. That's a V, sorry. That's 4, right? That means it's Ti plus 4. Right, so how many chlorides do you need? Chloride is in the, it's in group 7A, so it's -1. So if it's -1 and titanium is plus 4, you need 4 chlorines, right? You need 4 of these to balance the electrical charge of the titanium forward. So that's why it's TiCl4, okay? Solid titanium chloride, that's what they tell you. Titanium is used in a lot of things now. It used to be a pretty rare metal. It's hard to get out of the earth. It reacts with all kinds of non-metals like oxygen. I think it's mainly oxygen, and so it's like tied up and it doesn't exist as a pure metal. So it takes some energy to liberate the oxygen, but it's an impressive metal because it's element, I think it's element 23. And as element 23, it's pretty light. It's not like a real heavy metal. So it's not real dense, but it's very strong. It just turns out the molecular structure of the crystal is strong. So it's a very strong metal that is stronger than aluminum. It's stronger than iron, but it's lighter than aluminum. I'm sorry, it's lighter than aluminum than iron, but it is heavier. It's more dense than aluminum, but it's much stronger. And so it's a very useful metal for use in, you know, initially they used it like in military applications, but I think they now actually put it like in aircraft and actually medical stuff, you know, because if you have an artificial hip, for example, that's made out of metal, you want to use something that's very strong and durable, but you don't want it to be too heavy so that you don't weigh an extra 10 pounds. So you use something like titanium, okay? So how do we get it? Well, titanium's a metal, so it's not a diatomic. It's a metal, so it's a solid. And then you got your chlorine. Chlorine's a diatomic. So what's the state of chlorine? Chlorine's a gas. Chlorine's a gas at room temperature. So just in terms of the halogens, fluorine is a gas, chlorine is a gas, bromine is a liquid, and then iodine is a solid. Okay, that's for the halogens. That's group 7A, just so you know. So it's the gas. So then how many do we need? We have 4 over here, so we need a 2 there. 2 times 2 is 4. Okay, so there's your balanced equation. You got the states of matter in there. That's your, so now any delta H for this would be delta H of formation under standard conditions. Okay, and so what do people do? They measure these. They actually run these reactions. They measure delta H, and then they tabulate them. You make these big tables of delta H values. Let me show you, I'm not going to show you the Alex one, but let me show you one just bringing up from the internet. Come on, here we go. Okay, so I'm going to come over here. Okay. Standard enthalpies of formation. And then we'll have a table in here. Okay. I'm going to plug in images so that you can see them. Okay. So let me come over here. Take a look at this. So if you do a Google search of standard enthalpies of formation, look what you see. You see all these tables coming up here, right? All these tables. It's a very common calculation in chemistry. So chemists actually use these values for all kinds of things. So we'll take a look at this last sort of step when we get there. So let me click on one of these so if we can see that. Okay, so let's see if this pops up. Okay, so here's one. This is just one table. So notice what they have here. They have the names of these compounds, right? So these look like organic compounds. At least some of them are. Ethane and ethanol and glucose and ethylene. Those are all organic compounds. But there's also some inorganic compounds like calcium carbonate, calcium oxide, carbon dioxide, ammonia. So those are inorganic. And then they give you the formulas, right? And their state. Notice how they put the states of matter in there, right? And here's your delta H of formation under standard conditions at 298 Kelvin. They did not write that it was at 1 atmosphere, but typically it's also at 1 atmosphere, okay? Now, see these values here, right? See how it has a value there? Some of them are exothermic, most of them are exothermic. Some of them are endothermic. Acetylene is endothermic, ammonia is exothermic, benzene is endothermic. In other words, when you form a mole of this material, you're going to have either an endothermic or an exothermic reaction. But what, see, it's not giving you an equation, right? There's no whole equation for that. It's just giving you the material. Well, what we just did, where we went through writing the equations, they're just showing you the product. So it's implied in these values that you took 2 moles of carbon, right? So 2C solid, and you took 1 mole of hydrogen plus H2 gas gives you C2H2 gas. So they're just showing you the products here. And that's convenient, right? So instead of having to write the whole equation and then looking, but it's got a different reactant, so now we can't use it. We all know now that these tables are associated with, element 1 plus element 2 plus element 3 gives you 1 mole of the product at 298 Kelvin and 1 atmosphere pressure, so forth and so on, okay? So these are called standard enthalpies of formation. Alex has a table of them. Your textbook has a table of them. The internet has tables of them. Be a little bit careful if you're on the internet, if you're Googling this stuff, because sometimes the units are different. So they might do it kilojoules per gram or kilojoules per kilogram. But the standard way that we do it in chemistry, actually, a more common issue is organic chemists, they will actually use different energy units. They'll use kilocalories. So they still do kilocalories in their textbooks sometimes, which it turns out it's kind of nice to do kilocalories because the numbers are nice and smooth. But in this course, we're going to do kilojoules per mole, okay? So I just want to make that point. So let me show you an example of how you use these. And I'm going to give you a little equation here, which is useful. So in general, the idea here is the following. You're going to have some reactant A with a coefficient, and then a reactant B with the coefficient, right? And you might even have a third reactant. So I'll put C, right? So 3 reactants, right? They're going to have states of matter, and then you're going to get products. DD plus EE. I'm just going pretty kind of crazy here. 3 reactants and 3 products. You're not likely to see 3 reactants and 3 products. You might see 2 reactants, 2 products, 2 reactants, 1 product, 3 reactants, 1 product, 2 reactants, but you're not likely to see 3 and 3. But I just want to kind of put it all out there, right? So for example, you might have, 6 CO2 plus 6 O2, I'm sorry, 6 H2O, 6 H2O. Goes to C6H12O6, solid, plus 6O2, gas, okay? So really what you're saying here is the coefficient is a 6, so A equals 6, right? Here the coefficient is a 6, so B equals 6, right? Let's ignore C, let's just go to the product here. D is equal to 1. We don't have a third product, we just have a second product. So here E is equal to 6, right? So these, A, B, C, D, E, F, lowercase, those are referring to the coefficients, right? And then the symbol capital A, capital B, capital C, those are the actual formulas that we're talking about, right? Those are the formulas, right? So here's the idea, okay? Now, what's nice about this is that we have a certain calculation we can do. If we want to know what delta H for this reaction is, what's delta H for this reaction? We could go out and do it experimentally, that's possible, but maybe we don't want to do the experiment. Maybe we're lazy and we just want to look up the value. You're not likely to find for every reaction the delta H for these reactions, but you can calculate them using the delta H of formation that we've been talking about, that table that I just showed you, right? You can use those values, and here's how you do it. Delta H of a reaction, and again, we'll assume that we're under standard conditions, is equal to the sum of the number of moles of each product, so NP, times delta H of formation of that P, of that product, P for product, minus delta, I'm writing a delta there, N sub R times delta H of formation of each reactant, R for reactant. So P is product, R is reactant. Okay, so this is the sum, right? This is, you know, mathematically this means sum, which means add them up. So let's come back up to this over here, and I'll show you what I mean by this. For that one, delta H of reaction, okay, I'm going to uncancel these. CC, F, F, right? Lowercase f, uppercase f, okay? So here's how you do it. You do the products first, right? So it's products minus reactants. Okay, so here, what I'm gonna do is you do the products first. So what you do is you take the coefficient D, whatever that is, it's a 1, a 2, a 3, a half. So you take that, and then you look up the delta H of formation for that one. So D. Okay, sorry about the F and the D. I don't want you to be confused by that. In other words, you look up the delta H of formation for that material. So for example, you look it up for that one, okay? So you take this times this. Then you add that to the next one. The next one is E. So E times delta H of formation of product E. Then you add that to the third one right over here. So you take F. So, you know, if the coefficient was a 3, you would put a 3 times delta H of formation of F. Okay. You add those all together. So let me put it in parentheses. Sorry, these parentheses aren't going to be great. I'll put it in brackets like that, right? So you're adding up all the products first, okay? Then you subtract. I don't have any room here, so I'm just going to write a subtraction there. You subtract the reactants. The reactants are A, B, and C. So A times delta H of formation of A plus B times delta H of formation of B, that's the uppercase B, plus C times delta H of formation of C. Put that in brackets too, right? So products, you add them up. That's what the sum sign means, the sigma, minus the reactants. You add up all the reactants, you add up all the products, and then you take products minus reactants. Don't do reactants minus products. It's a very common error. Do products minus reactants, okay? And then that will give you delta H to the reaction. So it seems like a lot of work, but it's only a lot of work because I put in 3 reactants and 3 products. It's usually at most 2 reactants and 2 products, right? You could even have 1 reactant and 1 product, and it'd be very easy, right? But products minus reactant. You look the delta H values up. You look them up in a table. Those are looked up in a table. And then these are just the coefficients in the balanced equation. And this will allow you to find delta H for virtually every reaction, right? Virtually every reaction, because there are tables of delta H of formation values for thousands of materials out there. The one that I showed you, it only had a few, right? It only had a few values, like a dozen or something like that, right? This doesn't have a lot, but there are, well, actually there's another group of columns over here, right? So it's maybe like 10 over here and 10 over there. So that's 20. But there are bigger tables where there's, you know, you can look them up and you got thousands of values, okay? So let's run it through. It's just a simple calculation, but you're going to make little mistakes when you do it. So you just got to practice them and you won't make the mistakes after you do it a few times. That's the important point. Okay, let me bring up this problem. Here we go. Okay, so calculating a molar heat of reaction from formation enthalpies, right? So you're using the formation enthalpies, the delta H of formation under standard conditions. You're using those values and you're using them to find the heat of formation, heat of reaction. So using the table of standard formation enthalpies that you'll find under the ALEX data tab, calculate the reaction enthalpy for this reaction under standard conditions, right? Everything's going to be under standard conditions for these problems, okay? 8 H2S gas plus 4 O2 gas yields S8 solid plus 8 H2O liquid, and then round your answer to the nearest kilojoules. So you don't need to have 0.3 kilojoules or 0.7 kilojoules, just round it to the nearest. So you look these things up. Now I do want to make a point that elements are zero, right? Because if you think about the way we defined everything, it was element plus element gives you a compound. So what we're doing is we're assuming the elements have zero value. So elements are zero. So if you look at this equation, S8, that's going to be zero because that's an element. O2, that's an element, so that's going to be zero as well. So really only the H2S and the H2O are going to have values. Okay, so let me practice this one with you. There we go. So the equation is 8H2S, which is a gas, plus 4O2, which is a gas, yields S8, which is a solid, and then 8H2O, which is a liquid. Okay, interesting reaction, actually. It's hydrogen sulfide plus oxygen forms sulfur and water. I wouldn't have guessed that. So this is a way to take swamp gas, which has hydrogen sulfide. If you ever go into like a little lake or a creek that's like the water is stagnant, it's not able to move, what happens is bacteria will grow in there, and the bacteria will, they'll produce H2S, and it stinks. It smells like rotten eggs. And that H2S, if it does come in contact with water, can actually be used to form sulfur, elemental sulfur. So this would be a way to isolate elemental sulfur. It's kind of interesting, okay? So you're gonna look these values up. So I'm gonna write the values underneath them, right? So I'm gonna write our delta H values. So these are delta H of formation for each of these. Now we know two of them already. This one's gonna be zero because it's an element, and this is gonna be zero because it's an element. So this one, I happen to know this one offhand. This is negative 285.8. By the way, the units of these are kilojoules per mole. Okay. All right. So the only one that I'm not familiar with is H2S. So you open that up. You know, you look at your table, open up the table, and it's negative 20.6. Okay. So there's our values, and that should be good right there. Okay. Water's known very well. So now we can go through the calculations. So delta H of reaction under standard conditions. So I'm going to do the sum. I'm going to do it on a separate line. Sum of delta H. Oh, I'm sorry. I wrote that wrong. Sum of the number of moles of each product times the enthalpy change of formation for each product. So I'm going to do products first. Okay. So It's balanced. So the coefficient for S8 is a 1, but the value is 0, right? 1 times 0 is going to give you 0. And then the coefficient here is 8. And then the actual value is negative 285.8. Okay? So it's going to be 0 plus an 8 times negative 285.8. So 8 times 285.8, but that's a negative. And you get negative 2286.4 kilojoules per mole. Some books, what they'll do is they'll say, hey, there's 1 and the 8, those are in moles. So moles times kilojoules per mole is kilojoules, and you get rid of the moles, right? It's just kilojoules. Other textbooks, they just have the coefficients being unitless. So it's just 1 or 8. And then they leave the kilojoules per mole in there. So it's not particularly a big issue. Alex will tell you what units they wanted in, okay? So there's your products. Now we do the reactants. So number of moles of each reactant times delta H of formation of each reactant under standard conditions, right? So now you got the reactants. So you got 8 times negative 20.6 plus 4 times 0, right? Again, one of them is 0. That's an element. So 8 times negative 20.6. So you get negative 164.8 kilojoules per mole. Okay, so now we got the reactants. And then remember, it's not reactants minus products, it's products, it's final minus initial. Products are final, reactants are initial. So final minus initial. So delta H of reaction would be products, so negative 2286.4 minus a minus 164.8, right? Minus a minus. So that means it's plus, right? So it's 2286.4, which is negative, plus 164.8. And you get negative 2121.6 kilojoules per mole. Okay? Exothermic, right? That's an exothermic reaction. So your final answer, oh, sorry, round it to the nearest. So negative 2122. Okay, it's actually pretty highly exothermic. So if you were to run this reaction, you'd get quite a bit of heat coming off. That's a highly exothermic reaction. I'm sort of surprised at that. Well, actually, no, because it's really combustion. Really what you're doing is you're doing combustion. The oxygen is reacting, so it's replacing the sulfur. So I guess that would be exothermic. So there you go. All right. Let's try one more. Okay, calculating a molar heat of reaction from formation enthalpies using the table of value, right? Same problem, right? Now this one is actually combustion of what's called ethane, C2H6. It's reacting with oxygen, which is O2. Now remember, combustion is generally exothermic. When you react with something with oxygen, it's going to be exothermic. So this is an exothermic reaction. You're going to get a negative delta H for this. It's probably going to be pretty big, in fact. But same idea. They're going to give you the balanced equation. It's ethane. So you just got to look these values up. Some of them I know, but I don't remember what ethane is off the top of my head. I think it's negative 74. It might be negative 74. It might be negative 80. Somewhere in the negatives, tens. Okay. So let's take a look. Okay, so 2. Now remember, this doesn't have to form 1 mole because we're not talking about the heat of formation. These are not heats of formation. These are just reactions, so it's just heat of reaction. Okay. But, you know, the 1 comes into play when you're talking about the heats of formation. Okay, so that gives you 4 CO2. And how many waters? 6. Okay. And then we're just going to look these values up. This one we know is a 0. This one we already did, negative 285.8. This one is negative 393.5, just so you know. And the only one that I'm not familiar with is the C2H6, but I think it's around negative, okay, negative 84. Actually, they're using pretty round numbers. So this one's negative. I think I've seen it as negative 84.06 or something like that. But this one, they rounded it off. Okay. So again, let's do the products, right? So you do the products first. It doesn't matter which one you do first, but you just got to make sure you do products minus reactants. So the products, you've got 4 of the carbon dioxide. So 4 times negative 393.5 plus 6 times negative 285.8. Okay, and then you add all those together. They're both negatives, right? So you're going to be adding negative numbers. So it's going to be a pretty big negative number. So 4 times 393.5 plus 6 times 285.8. So you get negative 3288.8. Pretty big values. So this is combustion. That's why we use combustion in automobiles and jet engines. A lot of energy, a lot of heat comes out. We can use that energy to do mechanical work. The reactants are easier because the oxygen is 0. So it's 2 times negative 84 plus 7 times 0. So that's what, negative 168. And then you're going to do products minus reactants. So you're going to take this number and you're going to subtract this number. When you're subtracting something that's negative, you're going to add it. So really you're adding a small number to a small positive number to a large negative number. So the large negative number will become a little bit less negative, but it'll still be a large negative number. This is a lot of energy. That's why ethane is useful for generating energy. So then you just do your products minus reactants. Okay, so notice I didn't put the formula in anywhere, but that's what we're doing, right? When we say 4 times this, we're saying, you know, N sub P times delta H of formation of P plus N sub P times delta H of formation of P, right? And then you're doing the sum, right? So you're adding them together. So this would be negative 3288.8 minus a minus, which is plus 168. So 3288.8 negative plus 168, and you get negative 3120.8, but that's easy to round. So negative 3121 kilojoules per mole. Okay, and there you go. And that's how you do it. It's a very useful equation, right? Delta H of reaction equals the sum of the number of moles of each product times delta H of formation of each product minus the sum of the number of moles of each reactant times its delta H of formation under standard conditions. That equation gives you this answer right here, right? So what it does is it gets you out of doing the reaction. You don't have to actually do this experimentally. You can just look up those delta H of formation values and then use this formula, and then you've got an answer right there. Okay, so there you go. That's the last section, 5.6. So that's pretty much it for chapter 5. It kind of lightens up a little bit at the end there, but good luck with working on these problems. And then on Monday, we'll come back and we'll start talking about gases, right? So the next chapter is chapter 10. So if you want to work ahead on chapter 10 this weekend, all of my videos from chapter 10 are still available from last semester on YouTube, and you can watch those videos and start working on those Alex problems. But on Monday, I will start lecturing on gases, which is a fun chapter. Okay, so have a great day. Have a great end of the week. It's getting busy here, but we're about halfway through this, right? This is the 3rd week, so we're halfway through, and we'll be done with this at the end of July. Okay, so take care.